Hello, everyone. We are doing model selection. We have many variables, like 50 variables, and we want to get rid of all the noise variables so we can present a small model that we can explain well. Small models are also called parsimonious models, so, which of course still has all the important variables. So we're doing the opposite now from the forward approach, where we added one variable at a time. Now we start with a full model and remove one variable at a time. And again, we distinguish between the modern approach using AIC and the traditional approach using p-values. So we start with the full model, find the single variable that when removed from the model reduces the AIC most. And if it doesn't lead to an improvement in the AIC criterion, we stop, or else we continue on and on until the model is empty. Probably you're going to stop sometime in between because the empty model is probably not good. All right, so as before, there is a variation of this approach, which is just to use the sequence of models generated by the traditional approach using p-values and evaluate that with AIC. Here we have the Bush example again, using R code. We have again the step AIC function here in R, and we just have a different direction now, direction backward. Again, we have the initial model, but the initial model is now full house, the whole thing. And the final model, what's left over. And 1, 2, 3, 4, I think this is the same model as we found before. It's not always the case. And here's what happened in between. Yeah, we're removing one variable at a time. And let's see, we're starting with the full model and then minus, meaning removing e-vote and removing votes changed and so forth. And then we ended at this value, and doing anything else no longer improved the AIC. Okay, so that's relatively straightforward. The traditional approach, again, straightforward. We start with the full model, and then we remove the variable that is least significant, which means which has the largest p-value, like 0.8 or some crazy large value like that. And equivalent to that is which reduces the R squared least, right? We know that these are equivalent things, so I can either talk in terms of R squared or p-value. And if nothing helps anymore, then we stop. All right, we have another clicker question. This is the same data as before. Same model even, I believe. Which variable is removed first for backward elimination here? And I'm giving you some choices. All right, I will leave you to answer this, and I'm moving on and show you what actually happens in practice. So again, in Stata, I'm using the stepwise prefix. I am specifying the probability to remove. So you see the PR. Before we had PE for enter, probability remove, also put in 10%. And then I removed one at a time. I'm removing e-vote. I think that's the same thing as happened with AIC, and so forth, until I'm now even removing income. And remember before, when we went forward, we included everything, and income was still hanging around because it was the most significant variable at initially at 0.0000 something, and then at the end at 12%. But now, as we're going backward, income is greater than, well, we have the 12% here, and which is greater than 10%, so we can remove it. So we end up with a different model. We end up with the model that has removed income, and then the p-values change again a little bit. So a different conclusion here. As we have seen, the two strategies, forward and backward, may not always yield the same result. And the more highly the axes are correlated with one another, the more likely are differences to arise. But not necessarily, right? I'm not saying every model has to be the necessarily difference. If all the x variables are uncorrelated with one another, no differences arise ever. That's the ideal case. Then regression is completely easy. But of course it doesn't happen, because that would be too easy, right? Okay. That's the end of this segment. This is already starting the next one. The end.